Alrighty, so welcome. This is what would have been my office hours. I'm gonna be going over um, the contents that are gonna be on the exam too. Please make sure you review all the videos, all exams, the homework problems, and even the clicker slides. So yeah, first I'll start by giving an overview of what you're gonna be having the day of the exam. You're gonna be given an appendix and a periodic table. In this appendix, you're gonna find the best pair theory chart. You're gonna find Avogadro's number. You're gonna find the polyatomic ions listed and etc. This is for chemistry 114. So yeah, so molecular theory is going to be an exam too. Molecular theory is all about the best pair theory. Best pair is valence shell electron pair repulsion. It basically predicts the shape of molecules in a 3D space, all relating to electron pairs, both bonding and non-bonding, such as lone pairs. I'm gonna be using lone pairs and non-bonding interchangeably because they are interchangeable. So yeah, just heads up for that. The molecular shape also depends on the number of bonding pairs and lone pairs, all right? And the main difference between electron and molecular geometry is that we consider all electron domains on electron geometry, so both bonding and non-bonding pairs. And in molecular geometry, we only consider the position of the atom that we're focusing on and ignoring its lone pairs, okay? But this is only for molecular geometry, all right? So let's practice a couple problems that I have here prepared already. Um, Alrighty. So how to start this? You are gonna wanna do three steps, I think. I'll count them as we go. So make sure you know how to use this equation, S equal n minus a. Because this is gonna help you draw the Lewis structures for these, okay? You don't really have to do the whole calculation, if I'm being honest with you. If you're not familiar with S equal n minus a, S predicts the how many uh, lines you're gonna be sharing, how many electrons in total you're gonna be sharing in a Lewis structure. The N is your needed, like so. The N is you get that from the periodic table, using the valence electrons, okay? And the actual is what you actually have in your structure, all right? So I'll do it for ClF3, but then I'm just gonna go quickly for the rest. So ClF3, I drew the main skeleton. How do I use S equal n minus a on this? So I do S equals n minus a, where n is you count how many things can fulfill the octet rule. So you have four things here that fulfill the octet rule. 4 times a, 32. Alrighty. If I had, let's say, like a hydrogen, hypothetically, I will have to add um however many hydrogens I have, which is 1, times 2, because only one thing in this structure will fulfill the duet rule. So you have to be wary of the things that you have in your structure, all right? Then these are, what is this? This is electron total. I really like to make up units because it helps me keep track of my things, all right? Then A is you count everything that you have in total. So in this structure, I have 3 fluorines. So 3 times the valence electrons of fluorine is 7 plus Cl, which is also 7. So you can just do like 4 times 7. So 4 times 7 will be 28. Alrighty. And S equal n minus a, where 32 minus 28 will be 4. And when you divide that by 2, I'm dividing it by 2 because there are 2 electrons in a single line in Lewis structures. So when I divide that by 2, it's just 2 lines shared. Now, you see this and you're like, that does not make sense. That is fine. This rule only applies to NOF, only to nitrogen, oxygen, and fluorine, all right? So you have to keep that in mind. Um, only to nitrogen, oxygen, and fluorine. So even if you calculate it and you're like, what the heck? It doesn't like, I have three fluorines. How am I going to have two lines? Sure, that's fine. This rule only applies to NOF. With that said, I will forget about N and I will forget about S. It does not, like, when I'm taking an exam, I don't feel like it's quite helpful. When I'm drawing a Lewis structure, I only focus on A. And A is what you count on your actual structure, like the electrons that you actually count. So far, we have wasted 6 electrons because you see the lines shared? Those are 6 electrons being shared throughout every fluorine and chlorine. So 28 minus 6, let's say, I have 22 electrons left to spare. And how do I make good use of that? Well, I start counting. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. You see that? So I had nowhere else to put my lone pairs in, and I can't violate the well, you can violate the other, I will say that. But for the sake of this, and to keep formal charges, normal and even, um, you will do two lone pairs on chlorine. I drew them as lines, but you can do this. It's the same thing. So this will be our drawing for ClF3. Now, the main question was determine the electron geometry and molecular geometry for the molecule. So what is the electron geometry? Like I said, you would focus on like count how many groups you have around the central atom. All right. So I have 1, 2, 3, 4, 5. I have 5 groups, which means that it must be trigonal bipyramidal. Okay. And then for the molecular geometry, you are going to be considering the electrons. Here, I did not consider the electrons. I'll show you. So I said that there were 5 groups. This is 2, 3, 4, 5, 6. So I said 5 groups, trigonal bipyramidal. Because there's 2 lone pairs, it will be T-shape. And does this make sense? Yes, it looks like a T. Well, an inverse T, but you get what I mean, right? It will be, so the molecular geometry will be T-shape for number 1. I'm gonna be cruising through for the rest because that took a little bit. So for NH3, all right, you will draw it like so. You are going to count again the domains, the environments, the groups, whatever you want to call it. Everything around that central atom, you have to count it to account for the geometry. Okay, so it will be 1, 2, 3, 4. You have 4 things, 4 groups, 4 environments, for whatever. It will be tetrahedral. The electron geometry will be tetrahedral. All right. Now for the molecular geometry, once more, if we are in tetrahedral and you have 1 lone pair, it will be trigonal pyramidal. All right. Sorry. All right. There we go. The next one is SO2. SO2 will be drawn like this. Again, you can do the S equal N minus A. It won't follow through, like you won't prove it because you have this one that can violate the octet rule, and it does so. It does violate the octet rule, having an excess of 2 electrons. Sorry. What else? You might have drawn it like this at first. Let me show you. Uh, da, 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 da. I think this cannot be, and I'll tell you why. I'll quickly explain. It's because of the formal charges. So when you're drawing Lewis structures, you also have to account for the formal charges. You don't want too many charges on your structure. For sulfur, it has 6 valence electrons, and I'm quickly calculating the formal charge. You have 1, 2, 3, 4, 5, 6. this will have a formal charge of 0. All right, and that's good. This one will have 1, 2, 3, 4, 5, 6, also 0. So throughout, I have 0 charges. Okay. I hope that makes sense. So anyways, you count the groups. It doesn't matter that they are pi bonds here. The double bonds are called pi bonds, okay? It doesn't matter that there are pi bonds in the structure. You still count it as one group or one environment. So this will be 1, 2, 3. When you have 3 environments, that is trigonoplanar, and the that's the electron geometry. For the molecular geometry, because you have one extra lone pair, so you have a group of 3, but you have one lone pair that will be bent. Does that make sense? I hope it does. Oops. And then lastly, for water should be an easy one, okay? So you try like this, right? So you have how many groups? You have 1, 2, 3, 4. You have 4 groups. It will be tetrahedral, but because you have 2 lone pairs, it's gonna be bent. And I'm sure you'll just know this by memory because it's a big structure that keeps coming up and up and up and up again. Okay. More questions about molecular geometry, but this time I ask for the approximate bond angles. So you see this PCl5, don't get scared. Please don't be scared. It can violate the octet rule because this is not N, this is not O, this is not F. It's phosphorus. So surely it can violate it, all right? And it does so. So you have, let me have some more space. You have, oopsies. You have 5 chlorines attached to this phosphorus. And I'm not going to draw the lone pairs because I'm going to be assuming that they fulfill the octet rule. Okay? And first, like I said, first step is draw a Lewis structure. Second step is count how many groups you have. So 1, 2, 3, 4, and 5. And when you have 5 groups, it will be, again, trigonal pyramidal. The molecular geometry of it will be also trigonal. Sorry, I said pyramidal. Trigonal bipyramidal. The molecular geometry will be just about the same because you have no lone pairs. And the bond angle will be 120 and 90 degrees. It will be 120 equatorial and 90 degrees axial. So equatorial is, let me see. There we go. So, okay. Equatorial, think about equator. It's like mid, right? In the middle. So this is 90 degrees equatorial. This is axial, right? So that's what I mean when I say that. Then I have SF4. SF4 will be drawn like this. Give me 1 second. My pen keeps like connecting, not connecting. Okay. SF4. You have this. Oh, what is that? What is she drawing? What are those dashes and wedges? You will encounter this in Oracle, hopefully. This just means that it's in the front. The wedge and the dash means that it's in the back in a 3D space. Okay. So, and I'm missing a lone pair. There we go. And first you count, you draw Lewis structure. Second, you count however many environments you have. You have 1, 2, 3, 4, 5. We said that when we have 5 groups, it's trigonal bipyramidal. But because you have here 1 lone pair, it will be trigonal bipyramidal seesaw. Okay, and it kind of looks like a seesaw. No, it resembles a seesaw in a way. No, the bond angle will be around. It will be less than 120 and less than 90 degrees. Why do I say less than and not exactly? And like, I'm not sure about it. It's because when you add lone pairs into an atom, it it changes the bond angle and it decreases it as long as you keep adding lone pairs into that atom. Okay, so it's not exactly 120 and 90 degrees. No, it decreases it because you have an excess of electrons. Okay, um, and then the same thing, you will do the same thing for IFCl2. This takes too long, so I'm not gonna do that. And I'm sure. Yeah, okay. Yeah, it's here, so we'll still draw it. So again, CF4, CF4, and it's asking if it's polar. Again, polarity, it's polarity means a difference in electronegativity, okay? So even though we are not giving numbers like electronegativity values, we can still make an estimate based on how electronegative something is compared to something else, okay? Um, so you will do this by looking at a periodic table. You know that electronegativity increases as you go from the left to the right, but also it increases as you go from the bottom to the top, from down to up. Okay, so it will increase diagonally from left to right, like that. Okay, um, and using that example, you can predict the electronegativity, like if it's polar or non-polar. Okay. I wanted to say that polarity. Also, think about a battery. When you have a positive and a negative charge on a battery, there is a partial. This is the sign for partial is delta. There's a partially positive side on a battery, right? It's not entirely positive and it's not entirely negative. There's a partial positive side and a partial negative side, all right? And we like to think the same for molecules, okay? So in this case, CF4, um, you have a partial positive on carbon, but you also have a partial negative on this fluorine. So the dipole moment, this is what we call a dipole moment. When I draw this arrow like this, that's a dipole moment. It shows you where the electronegativity, or it shows you where the most negative charge is going toward, okay? And in this case, I'm saying that the most negative charge is going toward the fluorine. And is this true? Yes, look at a periodic table. It is true. Fluorine is the most electronegative atom in the periodic table, and it is more electronegative than carbon in this case. So electronegativity will flow towards fluorine. So if we draw like that for all of them, we see that first this can cancel out because they're going opposite sides. So the negative charge is going toward the fluorine, not the carbon. So they're going opposite sides, they can cancel out. And the same things for the ones that are vertical up here, they can cancel out. So will you say that this is polar or non-polar? I think it will be non-polar because there is no dipole moment, okay? Because they're all canceling each other out, right? I hope that made sense. I can show you a polar one. Just give me 1 second. Let me erase this. Um, let's do NH3. Next one. If my pen allows me to. Alrighty. NH3. NH3, you have um, the partially negative side here, the partially positive side here, and I'm gonna do that for all of them. Drawing the partial charges on your atoms really helps you visualize where your arrow will go. If you're not really comfortable using that arrow, again, the arrow is not scary, it's not gonna bite you. It is going to help you determine uh, whether there is a dipole moment or not. Okay, so for NH3, um, we can say that electronegativity will flow this way, upwards, but it can also flow this way and also this way. So overall, it's going like this. All right, it's going toward this lone pair. So yes, this specific example, NH3 is polar. Then the next one is, oops, SO2. Dun, dun, dun. Mm-mm-mm. Alrighty. So same thing. I'm trying to pick a different color. Um, it will float this way. Float this way. Sorry. There we go. There's a partial, very partial positive here. Because oxygen is still electronegative, but compared to sulfur, it is partially positive. Uh, Therefore, sulfur holds the negative charge better. Uh, and also, it does so. Like I'm like questioning, like what does it? But also because you have lumpers here, so that lumper will also help hold that charge better than oxygen would, and it will be polar. For the last one, Ooh, I meant to change this. This is not this. This is gonna be XeF4. Okay, XeF4. How do you draw that? You can do the S equal n minus a, like I showed before, but generally, this is what you want to draw. When you have your lone pairs like this, opposite of each other, that should be an instant, like, it's nonpolar, okay? And I'll show you why. So electronegativity will flow this way towards the fluorine for all of them, so, because it's the same fluorine. Come on now. And you're like, okay, well, this cancels out because they're opposite of each other. This cancels out because they're opposite of each other. Then you have the lone pairs, and you're like, what the heck do I do with this? They're also canceling each other out. So you see here, all right? So non-polar. Okay. The next question is asking about the next set of questions are asking about the molecular weight of the various compounds that I wrote. Um, Molecular weight can also be referred to as molar mass, MW, whatever, same thing, interchangeable. So how do you do it? First, I put them like this in the name form because to practice how to convert them into their symbols, their respective symbols. So first you have vanadium 4 nitride. You have to realize that this is not nitrite. This is ide. All right. So it will be vanadium. We know that the symbol is B. And then we know that nitride is just nitrogen, right? The charge on nitride, let me pull up my periodic table on my phone. The charge on nitrogen would be -3, right? I like to draw charges in a parentheses. And then we're told the charge of vanadium. Vanadium has a +4 charge, okay? Now, I use different like symbols, like parentheses, just to tell the difference. Parentheses are for charges, brackets are for amounts of the atom that you have in the compound. So if you have something that is +4 and something else that is -3, and you want to cancel it out to equal to 0 in the end, what do? Well, you multiply each of them by the least common factor, right? The least common multiple, sorry, the LCM. So that will be for nitrogen, it will be, again, brackets for amount. It will be 4. And then for vanadium, it would be 3. All right? And people like to do the crisscross. I like to do the cross because it just shows you the math. You see that you have 3 times 4 plus 4 is just +12. +12 minus -3 times 4 is minus 12. And when you subtract plus 12 minus 12, hang on. I'm like, what? Is this true? Yeah. Yes. Okay. What I'm saying is that it will equal to 0. Okay. So it will be b and 3 and 4. Uh, I can double check the vanadium 4. Wait, hang on. Dun 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 dun. B and 3 4. Vanadium 4 nitride. Yes, perfect. It will be B and 3. There we go. Um, what else? Sorry, that like me explaining it made me overthink a little bit. Um, then you have tin. Okay, people get confused for this one. I understand why, okay? No shame. If you see tin, you might instinctively think Ti. Ti is the titanium. Then you're like, okay, then what the heck? It may just be SB. SB is antimony. The symbol for tin is SN, okay? And then you have phosphate, that is a polyatomic uh, ion, all right? PO4. Uh, Hang on. I'm like, PO4 what? PO4 minus 2. I'm like, I don't wanna, I don't wanna say the wrong thing. Um, and then you have the charge of, sorry, PO4 minus 3. Sorry. Then you have 10 charge of plus 4. Um, so you write the charges in parentheses. Then the amount will just be in brackets. Again, these come up multiple. For phosphate, it will be 4. So you will do parentheses 4. And then for tin, it will be 3. So you will do 3 here. It's like a crisscross, but I show the math. I show why there's a 3 there and there's a 4 in phosphate. Okay. Um, and the same thing for, oh, I'm not writing these. Sorry. I said and sorry, vanadium nitride 4. Okay. SN3PO4 4. There we go. And then the last one, there's a charge of 3 in iron 3 phosphate, and we just use phosphate, which is -3. So there's nothing to do here. Like they cancel each other out, and that equals to 0 when you add these up. Sorry, not minus. You add them. That's why I was confused for this one later. Earlier. Um, when you add those charges, it will equal to 0. So there's nothing else to do here. So it will be FPO4. Okay. Now to do the actual math of calculating the MW. MW is just the sum of every atom that you have present in your molecule. Okay. Um, I am not going to go through all of them. That will take too much, too long. So, I can go over how to do it. The MW for the first one, vanadium 4 nitride, it will just be 3 because you have 3 times the mass of vanadium, okay, plus 4 times 4 because you have 4 nitrogen, 4 times the mass of nitrogen. And that will be your molecular weight. And then you will do the exact same thing for everything else. And you're like, okay, how do I do it for the phosphate when it's like in a parentheses? Well, let me ask you something. Let me see. 1 plus 6. When you see this, what do you do? Obviously, you do panda, so you will do the parentheses first. Okay, whatever. But if you see something outside of a parenthesis, you want to multiply it. So multiply that 4 by this other 4. You're gonna have not 4 oxygens in that molecule. You have um a holy crap. You have 16 oxygens in that molecule. All right. Please never forget about multiplying from what's inside the parentheses. And the same thing for the iron 3 phosphate. Now it will take too much, but it will take too long, so I'm not gonna go through it. This is the mole. Is asking how many phosphorus atoms you have in a specific sample of 9.17 grams of tin 4 phosphate. We just did this. This is SN3PO4. 4. Okay. Um, and I did calculate in advance the molecular weight of this. Alrighty. Okay. Now, what do you do? How to solve this? How do you even start with this? We'll start with the given. That's the first step. So, first step will be this: get the molecular weight. First step, matter of fact, is make this into like the symbols. Like put them, tra- translate name to symbol. Okay, or however you want to phrase that. Sorry, brain not working. Um, Second step will be calculating molecular weight. Okay. Hang on. I need to. Dun, dun, dun. Okay, sorry about that. Um. Uh, okay. First, you start with your given, which is 9.17 grams of SN PO4 4. Okay. Um. Help! I'm like struggling. I'm like, can you hear me? Uh. Alrighty. So start with your given. Make sure that you are writing the units that you are gonna be using because you want to keep track of them. Okay. Um, we're gonna be going from gram to mole to molecule to or to formula units. Oops. To formula units to a phosphorus atom. So how do you do that? Start with the given, which is 9.17. My goodness. I swear, this thing gonna be the end of me. Okay, 9.17 grams of tin 4 phosphate. Then you're gonna compare that to mole using the molecular weight. Okay. Um, the molecular weight will go like the 700 736.02 will go below because this is gram per mole as you see. So it's like saying 1 mole over this many grams as you see. Now write the units completely so you keep track of everything. I highly advise it. It will do you good. Um, this is taking my own advice. This is 1 mole of tin 4 phosphate. Okay. Then, like I said, you are gonna want to go to uh formula units or uh however many atoms you have of something. Okay. So first you do how do you do this? Let me see. What's a better way to explain it? 6.022. You use Avogadro's number. Don't forget it. Times 10 to the 23 formula units, or you can say atoms of P and 1 whole um, mole of P. Okay, And you're like, okay, well, how do I cancel those units? What? You're giving me units. Well, you could have done this one first. The 4 moles of P over 1 mole of tin 4 phosphate. Yeah, this will make sense to do it first better. But it's the same thing essentially because this is canceling out grams to grams, canceling out. You're canceling out the mole right here. I write mole in N, same thing. And you're canceling out this. So you have in total the atoms of phosphorus. Okay. Um, I think I have another one of these. I can explain a little bit better, maybe. Um, you have how many oxygen atoms are found in 30 in a sample of 33 grams of manganese 2 sulfite. Manganese 2 sulfite is just oops, is Mn, not Mg. Mg is magnesium. Uh, Mn is manganese. SO3 uh minus 2, and then you have charge of plus 2. I wouldn't have to do anything here, so it's just MnSO3. Okay. You start with what you're giving: 33 grams of manganese to sulfite. Um, and uh, then you're gonna go from gram to mole. So you're gonna use the molecular weight of manganese to sulfite. You're gonna find that it will be around 435 grams. 435 grams of MnSO3 over 1 mole of NnSO3. Alrighty. Then you want to find oxygen atoms. Okay. So far this cancels out. This cancels out. How do I cancel out the 1 mole of Nn? So you're gonna write it down here. 1 mole of um MnSO3, you're gonna count however many moles of oxygen you have in this compound. Okay, so hang on. Dun, 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 dun. Okay. So you count however many oxygens you have in the molecule. You have 3 oxygens total, so you write 3 mole of oxygen. This will be fine if it was asking you for moles, but it's asking you for atoms of oxygen, like the specific amount of the oxygen. So you're gonna do another step, another extra step, and you're gonna use Avogadro's number, which is 6.022 times 10 to the 23rd power. Um, and these are formula units of oxygen or atoms of oxygen. Um, you have this many atoms of oxygen in 1 mole of oxygen. So see how this cancels out, right? And in total, I'm not sure the answer. I wrote it down like the final, but it will be no, sorry. It'll be 1 times 44 times 10 to the 23rd power, oxygen atoms. That's your final answer. So if this is too confusing to start with, draw a roadmap. Personally, roadmaps confuse me even more. Like I get the first few bars and then I get lost. So I do this using units because units are really helpful. So roadmap will be gram to mole to mole of oxygen, like we see here. Then we're going to the uh, particles, which are oxygen atoms. Okay, like the specific amount of whatever is asking you, whatever particles is asking you. In this case, oxygen atoms. Um, this one. This is an stoichiometry question. The first step will be to balance the chemical equation. Is a balance. Well, look at it. You have four hydrogens here, five makes sense. Checks out, checks out. Okay, it's balanced. If you didn't know what I'm doing, I was just counting however many atoms I have on the product side and on the reactant side, seeing if it's equal to each other. And in this case, yes, it is. So how do you start this question? Um, well, it's asking you how much methyl bromide can be made if you have a 78% yield of the entire reaction when you have 13 grams of methane and 21 grams of hydrobromic acid. So what is what? What the what? Um, so again, we'll start with this. We'll identify things as we go. 78% yield. That is not theoretical. That is our actual. I mean, sorry. That is our percent yield because we know that percent yield uh, is what do I do? Percent yield is actual over theoretical. Yes. So this is percent yield. What else? What else can I say? Uh, you want to know how much methyl bromide is made. So buckle up because it's a long one. So you have, oops, can I write please? You have reactant number one. I'm gonna name this. Oh, hello. Can I write, please? This is, sir. Okay. Oh my god, it's literally not letting me write. Oh my god, this is funny. Hilarious. Oh, I love this. 1 second. Okay. Oh my god. This interesting. Okay, all I had to do was restart the program. Hmm. So this is my reactant one, this is my reactant two. So reactant number one. I start with 13 grams of methane. Methane is CH3. Sorry, CH4. Brain, please. Um, and you're gonna convert that to moles because we're talking in grams. So you're gonna have to find the molar mass for every single thing. So this is why the mass is given for every atom, every respective atom. I calculated it ahead because it will take too long in video. The molecular weight of that will be 16.042 grams CH4. I'll write all units so you follow along. Over 1 mole of methane is over its molecular weight. And that equals to 0.81 mole of methane. Okay. This is not what it's made. I'm just translating. I like to call this translate like the translation part because we started talking in grams and we need to start talking. We need to learn how to speak in moles. So that's what we just did. Now you're gonna do a second calculation, which is to know what you actually made using 13 grams of methane, or in other words, 0.81 moles of methane. So you start with 0.81 moles of methane, and here you're gonna do a ratio, a dimensional analysis of the stoichiometric uh, numbers here. Because this is balanced, everything has a 1. Okay? There we go. Everything has a 1. So if I'm writing the ratio here, it will be 1 mole of the product that we're focusing with. And you're like, we have two products. We have methyl bromide and we have hydrogen. Which one do I focus on? Well, what is the question asking you? You can focus on both. That will be great. It will still give you the same limiting reagent. But the question is asking you for methyl bromide. How much is made? So I'm gonna be focusing on that too. So CH3Br over 1 mole of methane, right? And that equals to 0.81 mole of CH3Br made. Alrighty. Now I'm gonna do the second part, which is reactant two, right? So the same exact process. Sorry, same exact process. Reactant two. Excuse me. You started with 21 grams of hydrobromic acid. So 21 grams of HBr, hydrobromic acid. We're speaking in grams, so we're gonna convert that to moles. The molar mass of hydrobromic acid is 80.908. If you get like 80.91, if you get 81 even, that's fine. It's just decimals. I'm using 5 6 for the molar mass. It's fine if you're using 2, whatever. As long as the numbers are within a range, it's fine. Okay. Um, so it's 80.908 grams. Please write grams of hydrobromic acid. And this is all in 1 mole. When you calculate it, you're going to get 0.26 moles of hydrobromic acid. Um, and then we just translate it, but we actually need to find out um, how much CH3Br would make. So we're gonna do 0.26 HBr, and we're gonna do ratios. Ratio is 1 mole over 1 mole. So 1 mole of CH3, which is the product, over 1 mole of HBr, which is here, um, the reactant. And when you put this in the calculators, as you can see, you can use your eyes as calculators. It's just 0.26 moles of CH3Br made. Now, when you look at these two, you can tell exactly, hang on, this thing here, like the control panel is, okay, I can see it. Here you can see which one is the limiting reagent. Which one do you make less of? Which one do you run out of first? You run out of the um, HBr first because you make less of it. Okay. Now using this information, I'm gonna change into a different color. Let's do green. Okay. So using this information, we're gonna move on to calculating our theoretical yield. Um, so theoretical yield. We're gonna be using our limiting reagent, 0.26 moles of CH3Br, and we're gonna be translating this from moles. I'm saying translating, but the wording is converting. I'm gonna be converting from moles to grams. So we're speaking in moles, but we gotta talk in grams again. Um, and because we are so fluent in grams, we already know the molecular weight of CH3Br, which is 94.93. Sorry, 94.934 grams of CH3Br. This is all over 1 mole of CH3Br. Okay, and this will give you 25 grams of CH3Br. And now you can move on to the last and final step, which is calculating the like how much metal bromide you actually made using the the 78% yield. Okay, I need to explain something before I move on to the last step. If if the percent yield of the whole reaction was 100%, it means that you made 100% of your product, this will be our answer. 25 grams of methyl bromide was made if there was an 100% yield of the reaction. But however, because there's not a 100% yield, there's a 78% yield, we have to calculate the actual yield, okay? Like the amount that you actually made um, in relation to the actual yield. So let me use orange. And we know that percent yield, let me move the arrow. We know that percent yield is equal to actual over theoretical times 100. We can manipulate this equation in a way that we can say actual yield equals all our theoretical here, times our percent yield divided by 100. So that's what we're gonna do. We have 78% yield divided by 100%, and the 100 is coming up from this that you're multiplying in the normal formula, um, normal equation, I should say. And our theoretical, we just calculated it. It was 25 grams. And from this, you will get about 19 grams of CH3Br that you actually made. So again, take a breather. It's not hard. It's just so many steps that you have to like memorize where you're going. Like, oh, I wrote, like, I balanced it, but then where do I go from there? Remember, you balanced it. You're speaking in grams. You want to make sure that you're speaking in moles, so you find out what you're making, how much of what you're making. So again, ah, I lost it. Um, Start here. Go from gram to mole. Then after you go from gram to mole, you use the mole that you see here and use a ratio to find out how much of the product you're making. After this, figure out which one is the limiting reagent. Remember, the limiting reagent is the one that you run out of first, so the one that you make less of. That will be your that will help you figure out your theoretical yield. And to figure out your theoretical yield, you have to go from mole to gram, and then go from there. Okay. Next is phase transitions. Phase transitions. Here we have a graph, a heating curve, uh, graph, and it's of a unknown substance, the substance X, and it's asking us the condensation temperature of substance X is at what temperature? Okay. For this, you're like, okay, how do I even, what, what is it asking me again? What? Where's my color? Okay. Um, One red actually. So first, figure out the phases that you have. So this is solid, this is liquid, and this is gas. Okay. When you are going from a solid to a liquid, what is usually happening? Like, think to yourself, what usually happens when you go from solid to liquid? Well, actually, you're melting. Okay. Oh, that's very light. I can barely see it. Let me try this one. Oh, perfect. You're melting. And when you're going to liquid to solid, think about of like water that you're putting in a freezer. You are freezing it. It's freezing. Okay. When you're going from liquid to gas, again, think about um evaporation. This literally what is happening. Liquid to gas is evaporation. Righty? And then vice versa. Gas to liquid Uh, that would be condensation. Think about uh clouds. Okay. The question is asking us where condensation is happening. Well, well, it will be around the temperature that you see here in between this line. It can be either condensation or evaporation. Okay. Um, it will be temperature 90 degrees Celsius. Okay. That's how you read this graph and that's how you interpret this graph. Oh yeah, this compound. Okay. I crossed it out earlier, a bunch of slides ago, because I knew it will come up again. So this is saying formal charge. It's saying consider the compound IFCl2. What is the formal charge on every atom? Okay, to explain this. How do I? Da, 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 da. Okay, let me look at my notes because there are two important equations that are good to keep in mind. Okay, period. You hear me now? Yay. Um, so formal charge is equal to, I found this equation in a textbook, in an organic chemistry textbook, by the way. This is like the year that I finally like when I was taking organic chemistry, I finally understood how to calculate formal charge because everybody was like eyeballing it, and I didn't like that. So I needed like a something to ground myself in, like an actual equation. So it will be valence electrons minus number of a non-bonding electrons, which are lone pairs. Um, I'm sure this is minus. I will check again when I do it. Minus one half of the number of bonding electrons. I mean, bonding electrons. Sorry. Again, valence electrons minus open brackets number of non-bonding electrons, which are lone pairs, minus half of the bonding electrons, close brackets. Okay. The other equation that you can use, the one that I never understood until I took organic chemistry and like I saw this and like everything clicked. It's just give me one second. Dun, dun. All right, it will be FC for Homer charge, balance electron minus electron in structure. Now you see why I was so confused. Like, what the heck does that mean? Electrons in structure. So I'm counting everything. What? So this first equation really put things in like into place, and it explained why we will only count one of the two electrons in a bond. Okay. So we are going to be calculating the formal charge of a. Give me one sec. My mic keeps disconnecting. I don't really understand. We're gonna be calculating the formal charge of chlorine. Um, it will be, like I said, balanced electrons is 7 for chlorine. To find balanced electrons, look at your periodic table and count uh the last how many electrons you have in the outer shell. So, however many boxes in the last row where you see that atom, count however many boxes until you get to the atom. Okay? So for chlorine, it will be 7 boxes. So 7 balanced electrons. It's a peculiar way to explain it. So 7 minus open brackets the number of non-bonding electrons. So for chlorine, you can focus on this one, this one. They're the same. You see how they have the same amount of lone pairs. It doesn't matter. So you have 1, 2, 3, 4, 5, 6. 6 non-bonding electrons. minus, I'm still debating. I don't remember if it's minus or positive. I'll tell you. Minus half of uh bonding number of bonding electrons. So 1, 2. Okay. So this is telling us that you have you have 1 times 2 is 2 divided by 2 is 1. Um, 6 minus 1 is 5. 7 minus 5 is plus 2. Now I can use the other one. I can show you how to use the other one. Fc of chlorine. Um, Again, valence electrons minus number of electrons in structure. So it will be 1, 2, 3, 4, 5, 6, 7. Okay, then it will be adding here. Let me see. Yeah, it will be adding. Okay, sorry. Sorry for that small mistake. It will be adding. Okay, make sure you change this to adding if you like this formula. It's adding, not subtracting, okay? Um, okay. So, again, I counted the lone pairs individually. You have 6 lone pairs here, but you have this bond to iodine, and you only count 1 electron out of those 2 electrons in the bond. And that made so much sense to me when I encountered this equation because it explained why you only count 1 electron out of the 2 in this bond, okay? You only count 1, all right? Um, so you're counting half of the bonding electrons. Alrighty. You can do the same for the rest. So I'll do the fast one because I swear to God, it's so much faster. But this one, equation 1 compared to equation 2, equation 1 gives you reassurance and it tells you like you're gonna get the right answer no matter what. Just make sure that this is plus. But you're gonna get the right answer no matter what if you do equation 1. Equation 2, you can also get the right answer if you use it correctly, if you know how to use it correctly, if you know why you're using it. Okay. So the formal charge of iodine, real quick, the valence electrons on iodine. I'm pretty sure it is 7, right? And then you count 4, 5, 6, 7, 0. Okay. And same thing for this one, 0. Oh, what happened? And the fluorine, 0. You have 4, 6, 7, 7 minus 7, 0. There you go. See how fast that was? Beautiful. You have the same question, calculate the formal charge on the oxygen atom of hydronium. We are smart people. We are quick people. We are intellectuals. We're going to do it for every atom. Okay? Using the fast one. Right? So, valence electrons of oxygen, real quick, 6. Right? You should know this already. You should memorize this. Use it so much that you just remember. Um, you have 1, 2, 3, 4, 5. So it's plus 1. Sorry. Formal charge of every hydrogen, because I'm saying every hydrogen because every hydrogen looks the same. It's literally 0. Valence electrons of hydrogen, 1 minus 1 of minus half of the bonding electrons, which is just 1. Whoa. Your formal charge is going to be 0. This explains the positive charge here because you have an overall formal charge of plus 1 throughout the whole structure. So answer should be this one. This should be a trend. You should start to notice this trend. When you notice an oxygen has 1 lone pair, that is plus 1 formal charge. When it has 2 lone pairs, 0 formal charge because you have, okay, let me write this example here. You have oops, you have oxygen here. You have 4, 5, 6. 6 minus 6, 0. So notice the pattern. You have one lone pair plus one formal charge. Two lone pairs, zero formal charge. Three lone pairs, you have negative one formal charge, okay? Um, so just wanted to say that. Um, what is the average NO bond order in the nitrite polyatomic ion? Oh, bond order, amazing. Okay, so for this one, the first thing that you should want to do is calculate the formal charges. If you have like multiple resonance structures, these things are called, right? Like this thing indicates resonance in a structure. So, uh, nitrite has two relevant structures overall. Um, but you should want to calculate the formal charge just to know if you have too many charges in a structure. I swear this mic of mine help. Um, so if you do calculate the formal charge, like I said, you see two lone pairs in an oxygen, immediate 0. For nitrogen, valence electrons is 5. 1, 2, 3, 4, 5, 0. Can I? Thank you. Um, negative 1. Oops. Can I write, please? Let me write negative 1. Um, 0, negative 1, and 0. Now, the formal charges are literally the same on both sides, so it doesn't really matter. The both structures are uh, relevant. Okay. Um, let me see. Okay, so I have two explanations for this. You can calculate bond order. Alright, you can calculate bond order using two methods. You can do. You have one NO, one NO that is a sigma bond. Sigma bond is just a single bond. Plus one NO bond that is a pi bond. And you have two total bonds of this. So 1 plus 1, 2. Whoa. Okay. No, that's not it. You also have to account for bond order when you're saying specifically bond order. A single bond is 1. Double bond is 2. Triple bond is 3, like the actual number. So you're gonna rewrite this thing. So you're gonna have um, one single bond is just 1, plus one double bond is 2. Okay, over 2. So 1 plus 2 is 3. 3 divided by 2 is 1.5. The other way to do this, which I like it's more it explains it better, really. Um, you have how do I do this? You have two relevant structures. Let me erase this. Should I? Yeah. Um, please. There we go. Okay, you have two relevant structures overall, and in both structures you only have one single bond, and you also have one double bond. Okay. Um. So to write this better, uh, you could do 1 over 2. Why 1 over 2? Well, for the amount that you have 1 in 2 relevant structures. You have only 1 sigma bond, 1 single bond in the 2 relevant structures, like you see here. 1, 1. 1 over 2 times 1. This one comes from the single or single bond. And the same thing you do. You only have 1 over 2 times 2 comes from double. Now let's say you had like 3 double bond, whatever. Yeah, I doubt you will have that many, but in the example that you see. But if you had 3 double bonds, well, you will change this one and you will put 3 here. Okay? Just in case you were wondering. So you do the math again. 1 times 1 is 1/2. 1 times 2 is 2. Divided by 2 is 1. 1 plus 1/2 is 1/2 or 1.5. Okay? Same thing, different ways to explain it. I really like this way better because you visualize it a lot better, right? What is the average NO bond order in in the nitrate polyatomic ion? For this one, you have 3 structures. 3 resonance structures. So you're gonna say that you have 3 um 3 NO bonds that are relevant, like you see. And in these 3 NO bonds, you have 1. Let me see. Dun, dun, dun. You have 1 that is a double bond, like you see in the structures. 1 double bond. But you also have, in every structure, you have 2 sigma bonds, right? All throughout. So 2 single. Okay, now you actually translate what double and single mean. So you have 1 over 3 relevant NO bonds times the double, which is 2, plus 1 over 3 times 1. Oh, sorry. You have two single bonds in 3 relevant structures. That'll be 1.33. And that's the bond order of the average NO bond order on nitrate polyatomic ion. Then these are, okay, this is explaining trends regarding boiling point and heat of vaporization. So when you have high intermolecular forces, IMFs, you have high boiling point and high heat of vaporization. Okay. What else? And vapor pressure will be low. And it's the opposite when you have weak intermolecular forces or low intermolecular forces. The stronger your intermolecular forces, the more energy that it will take to separate those molecules. So the boiling point should be high, okay? And like I just explained, the heat of vaporization should be high, vapor pressure should be low. And the opposite for the lower intermolecular forces, because molecules are a lot easier to quote unquote get rid of or break, or just they escape a lot easier when you have low intermolecular forces. The next question and last question really is this one that I pulled from the exam practice. I went over it It is so many things are wrong with it. My goodness. The question is asking what are the bond orders of N to N, and like a single bond of N to N and a single bond, not even a single bond, just the bond of N to N and O to N. What are the bond orders in a bromate ion? And then it gives you the resonance structures for, uh, uh, what is this? Nitrous oxide. Um, Hilarious. N2O. So how do I did this? I went over it so many times. I was like, I'm going freaking crazy. Like what? Uh, wanna use a pointer? Can I use a pointer, please? Okay, I can't use a pointer. I'll just present it. Go from here. Beautiful. Please, can I point? Okay. Um, so you have this resonance structure of nitrous oxide. Let me look that up. Let me make sure I'm not saying the wrong thing. Uh, into yes, nitrous oxide. Um, I discarded this uh structure, which was part of the resonance structure. Yes, it's still a resonance structure, but it doesn't. It's not relevant when you're calculating the bond order because you have too many formal charges. That's why it's important to calculate the formal charges. Okay, so I calculated formal charges of each. Here I have a -1 formal charge on this oxygen. As you see, it has 3 lumpers, so it has -1. You have 3, 4, 6, 7. 6 minus 7, -1. For this nitrogen, it will be 1, 2, 3, 4. 5 minus 4 is +1. And here, 2, 3, 4, 5. 5 minus 5, 0. For the next resonance structure, it has -1 charge on this one because you have 4 lumpers here for electrons. 4, 5, 6. 5 minus 6 is -1. You have 1, 2, 3, 4 electrons here. And 5 minus 4 is +1. And this one is 6 because you have 4, 5, 6. So 6 minus 6, 0. Um, I'm pretty sure I just said 6. This is formal charge 0. Anyway, it's asking for the bond order of N to N and O to N. This to this and this to this. How to do that? Well, I just said use the way I showed you a couple slides ago. You have 2 relevant NO bonds in these structures. You have here, 1 here, and 1 here. And, well, I'm going to explain the N2N first. So you have 2 relevant N2N bonds in the resonance. And you have one that is a double bond, and you have one that is a triple bond. Now, uh, only one of this, so 1/2 relevant NO N2N bonds, sorry, only one of the 2 relevant N2N bonds is a double bond. So it will be 1/2 times double plus only one of the 2 relevant structures has a triple N2N bond. So it will be 1/2 times triple. When you translate what double and triple mean, it will be 1/2 times 2 for double, plus 1/2 times 3 for triple. The bond order of N to N in nitrous oxide will be 2.5. Now for NO bonds in nitrous oxide, the bond order will be as the following. You have 2 structures, right? 2 relevant structures that have 2 relevant bonds that you're interested in, which are N2O or O2N, whatever. And only one of these two structures, or yeah, only one of these two relevant structures are single bonds. So you see here. Sorry, here. Only one of these two relevant structures or relevant NO bonds are single bonds. So it will be only one of the two relevant bonds, 1 over 2 times single, because it has only one of these two has a single bond. Plus the same thing as we did before. Only one of these two has a relevant um, a double bond in the NO bond. Okay, so 1 over 2 times 2 for double. When you do the math, it will be 1.5 for the bond order of N2O in nitrous oxide. You can do it even a lot faster, quote unquote faster. But you can also explain this as like this one. You have two relevant NO bonds. Oh, I only did it for NO, sorry. But you can do it for N to N as well. But uh I said I said that two relevant NO bonds is because you have one single NO right here and you have one double right here over two relevant bonds of NO, 1 and 2. Now you just translate what single and double mean, which is only one is single plus only one is double over 2. And it's literally the same thing that I explained here. Which is just 1 plus 2, 3 divided by 2, 1.5. And that's how you will solve it for this one. Oh, I did do it. Okay. See, yeah, I was so pissed at this question, genuinely. Like, what the frick? Um, like, it's so misleading. It was asking you for bromide ion, but it was asking you for the N to N bonds, like what? And then it gave you a structure, it gave you the resonance for nitrous oxide, like what? So I was like pissed. So I even did it for the bromide ion. So you have a bromide ion, which is BrO3. I'm gonna go out of like how do I exit this? Hang on, because I need to explain why I drew it like this. So let me draw. Okay, beautiful. Bromide ion is BrO3 minus. Um, if you do the S equal N minus A and only focus on A, which is your actual electrons in the structure, you're gonna calculate 26. Make sure you're not forgetting that minus. It means that you're gaining an electron, so you're gonna be adding it into the actual. So it's not 25, it's 25 plus 1 because of the negative that you see right here. And it's gonna be 26 electrons in your structure that you should be counting in the structure, okay? Um, what else? Okay, so when you do count it, you might draw the structure like this. Can I draw, please? BR. I'll draw like here. So far I've used 6 electrons, and I want to count up to 26. So, okay, a smart thing that I will do is fulfill the table for everything. Beautiful. I have 24. I counted it. I counted it. I counted the electrons very fast because this is an octet rule, 8 electrons, and you have 3 of them, 3 oxygens, so 8 times 3, 24. Okay. Now you say 24, so I will only need 2 extra electrons that I have to spare. It will go as a lumper, right? Yes and no. So the lumper is correct. It's a good move. However, you have too many charges in this structure. As you see, you have 3 lumpers for every oxygen. This is -1. This is -1. This is -1 for one charge on every oxygen. And on top of that, hang on, let me pull up my periodic table so I don't tell you wrong information. On top of that, The valence electrons on bromine is 7. If you count the formal charge for bromine here, you have 1, 2, 3, 4, 5. 7 minus 5 is -2. Do you see the problem? You have too many formal charges. We don't want this. We want to avoid this at all cost. So what do? You resonate it. You you stay with the electrons that you have in your structure, but you change them. So you have these lone pairs that can sort of form a pi bond between bromine and oxygen. So I'm gonna get rid of this lone pair, and you're gonna have a new bond here. That is the oxygen and bromine. And you count that again, and it's like, let me see, 26. One. Okay, count the formal charge on the bromine. You have 1, 2, 3, 4, 5, 6. You have -1. Um, Again, still too many. You can definitely decrease that formal charge. And you can definitely keep giving this bromine electrons because it can violate the octet rule. It's not nitrogen, it's not oxygen, and it's not fluorine. It can definitely violate that octet rule. So you're gonna make another pi bond here, and now you count formal charge for bromine, which will be 1, 2, 3, 4, 5, 6, 7. Is it done? Yes, it's done. You have zero formal charge here. So that's why I wrote it like that in the pink. Okay? You have a zero formal charge on the bromine. You have you have a zero formal charge on the oxygen and this oxygen as well. But you have a negative charge here, which explains why it is BrO3 minus. When I do the I'm not too sure. I'm not too sure if you had to draw the resonance structures for these, but for what I saw, what I'm seeing right now, and what I did calculate it to, um, I saw the bromide ion. I drew it, and I said that there are 3 Br2 oxygen bonds, 3 relevant bonds. Um, 2 out of these 3 bonds are double bonds, and so plus 1 out of these 3 bonds are single bond, like you see here. So it will be 2/3 times 2 plus 1/3 times 1. It's 1.66666, right? So that's the bond order of Br2O, not N2O, for a bromate ion. Yeah, that will be all. Oh, I did have this question. You can try it out. I'll look at the answers. I was trying it out to see if it will fit. I don't think this will show up in the exam, but it's nice to practice. It's from chem.libertex.org. Um, yeah, with that said, please study a lot. Uh, have a good one and take care of yourself. Bye bye.